Hi there. Welcome to Building Progressive Web Apps with the ArcGIS API for JavaScript. My name is Rene Rubalcava. I'm a developer on the JavaScript API, and I'm joined by Andy Gupp, as well as Thomas Other. So here's pretty much what we're going to be talking about today. We're going to be talking about what is a progressive web app. We're going to talk about some of the requirements needed when you're going to build a progressive web app, or essentially what you would do so you can call your app a progressive web app. We're going to talk about building progressive web apps with the ArcGIS API for JavaScript, and as well as mobile web performance, so some considerations there, as well as some really cool things you might want to take into account for 3D performance when building apps in general. So what is a PWA? All right, so if you've ever gone to a website on your phone, you might have gotten prompted to add that application to your home screen. And then once you do, it's going to go ahead and add an icon on your home screen for you as well. So progressive web apps are apps that essentially behave like native apps. They get added to the home screens of your mobile devices. However, what's really cool is they actually get run in a sandboxed environment, right? Which means that they're running outside the regular browser environment that you would use on your phone. You can do some really cool things with them, and they're meant to be performant so that they could run pretty well on devices. One of the things that they provide is smooth transitions. So as you go from page to page, or as you are scrolling through the page, everything looks really nice. It's responsive. The main thing here is that you try to get it fast loading. You want to try and have considerations for people that are not on the latest generation, newest phones that are probably more powerful than computers that you had a few years ago. Right, you want to be considerate of people that are on normal, low-budget devices. They also provide a native look and feel. I have a screenshot here of the Vitamix website. The Vitamix website is actually a really, really nice progressive web app that I recommend everyone to kind of check out just to see how well it performs on your devices. All right, so what are some requirements to be able to call your app a progressive web app? All right, so there's the idea of purple. You want to push critical resources, right? So this is going to be anything like the very necessary JavaScript, as well as CSS and HTML, just for the page to load, right? What do you really need to get started? Render the initial page or route, right? So this is where you want to take into consideration, do I need to have the map up front? Can I have maybe some sort of other form or other UI before a user's introduced to the map, if you're building mapping apps? You also want to pre-cache most of your assets, and that is something that you can do. We'll get into how that works in your application. So you're going to pre-cache the critical resources, which would be the JavaScript, CSS images as well. And then you want to try and lazy load the rest of your application. So if you don't need to display all of the images for your app because maybe people are going to scroll through it and they'll get to them at some point, you can lazy load those images, as well as the JavaScript, which is pretty critical with the API. You want to lazy load as much as you can. So we have our critical resources, JavaScript, CSS, render them to the page, and then pre-cache all those resources as well. And of course, then you want to lazy load anything after the fact. So service workers, important to note here, service workers are not a web worker. They actually behave a bit differently. They allow you to control and cache your network requests. So you actually have the ability to intercept the network request and to cache those results from those requests, meaning that if someone makes the same request later in your application, then you can go ahead and return the result you already have. It also is useful if someone uses your app, closes it, and it comes back and starts it up again. You have the initial requests that they made already cached in the service worker, and you can use those. So service workers have a series of APIs. There's the notification API, which is the one that will send notifications to your desktop. These are also the ones that can be pretty annoying when you go to a website and they kind of prompt you that they want to send messages, and you pretty much just push block all the time. They can be useful if you're building some mapping applications. In some cases, they can be useful to let the user know that maybe data has been added to a feature service that they might be using. You can do a refresh on that feature service, check to see if it's been edited or not, and then let the user know that there's new features or features have been removed or something like that, right? You have that capability to do that. The push API, pub sub capabilities, so you can subscribe to different things happening in the service worker. Background sync, this is usually useful for offline to ensure the data is being sent once you actually get a connection back. It's not something that you can really use too often with the JavaScript API, making maps, something like that, because trust me, I've tried it, and doing offline with a web app for JavaScript API and mapping and stuff, it's just too difficult. You're better off going with the native SDKs are built for offline capabilities, so you really should be looking there for that. Channel messaging, so communications with other things like iframes or other tabs or something in your browser, which is something that you can use. It's kind of cool. So one of the main things you want to do when you're looking at building a progressive web app, remember, we want to try and render the page as fast as possible. So you want to provide what is referred to as an app shell. And this is a kind of a page you might see when you first load up a site where maybe it's got placeholders for images, placeholders for text. They're going to be there. This is so that there's something visible on the page that we know something is happening, right? So it's useful for fast loading. Very minimal amount of HTML, JavaScript, and CSS just to display the page, get things going, load the resources you need, and then actually display some real data. So when you want to use something like this, you want to use this when the UI doesn't change very often for the initial page your user is going to get. You could do something really cool if your page is completely map-based. Maybe you want to display a picture of a map. Not a realistic one, but just some sort of a logo or image of a map that kind of lets users know, oh, a map is going to go here. Right? That would be kind of cool. And it separates content from the navigation, right? So you're going to move from one page to another, and you can have this kind of app shells working for the users, just so things are showing up. Manifest.json. So you want to provide this manifest so that the devices and the browsers know information about your app, right? So defines how the PWA is going to behave when it's installed as a home screen app. You define what the name is going to be, for one thing, which is important, right? You don't want to leave it just called name. Any icons you're going to provide, which you do want to provide icons. And ideally, you would provide multiple sized icons depending on the devices users are going to have, as well as the resolution of those devices. So you want to give them some options. That way, your icons will look nice on the device and not be all pixelated. You can define some themes for your application. This is going to theme things like the toolbar, scroll bars, and whatnot. Well, I don't know if it does scroll bars, but I know it does toolbars in the application, like where the URL bar would be and stuff, the header area, and any kind of display information for the app as well. All right, here are some progressive web app tips, things that you should know about. Native image lazy loading. So this is something that's somewhat recent with browsers. It's built into modern browsers. One of the things you can do is you can specify this loading lazy attribute on your images, and that means that image is going to go ahead and get lazy loaded. You can go in and wrap that in a picture tag, and when it's wrapped in the picture tag, it'll go ahead and you can provide the source with some media queries, and then the image tag in here. So you have a default lazy loaded image, but then you've also got a image tag here for the source media that based on the media query is going to display that particular image, right? So you can have multiple different size images for the same picture tag, I guess you want to say, right? So this is really cool. It's really something I recommend that you take advantage of. This kind of plays, we'll see it again in a second, but this kind of goes hand in hand with intersection observer, right? So essentially, JavaScript can do just about anything, right? So what's really cool with the intersection observer is that this is a browser API. You create this intersection observer. You define some entries for it, which is going to be a function, and then you're going to do something with those entries. In this case, I'll just log them out. But what you want to do is you want to observe the element, right? So that observe is going to happen the entries is going to get called whenever that particular element becomes visible on the page. So this is really useful for scrolling through a series of images, right? So as you scroll through a series of images, you get to the last image, maybe that you've downloaded, and then as you get to the last one, or maybe the second to the last, you go ahead and say, okay, I'm almost at the bottom of my page. Let me go ahead and fetch some more images or data, right? So this is used a lot in things like data tables. So you don't need to download all, say there's 5,000 records for a search result. You don't download 5,000 records. You would download maybe the first 100 or two. And as you scroll through that table, you can go ahead and say, okay, I'm getting to the bottom of my page. Let me go ahead and fetch the next 100. So you can do pagination based on the scrolling, which is really useful. And this is kind of how the intersection observer comes into play. And you can see how you can observe elements to find out when they're going to be visible, stop observing them, and then disconnect entirely, right? So that's a really cool API. WebP images. So WebP is like an optimized format for devices. It's really kind of championed by Google. If you run any type of PWA audits on your applications, you'll probably get some sort of a warning or something telling you that you can improve your audit score by adding WebP images. And this is how you would do it. You'd have a picture tag, you'd define a couple of source tags, one with the JPEG version, another with the WebP version, and then you have your image source tag, and you can have the default be the JPEG version. And the way this is going to work is that if the browser supports WebP, it'll use the WebP image. And if it doesn't, it'll just fall back to the JPEG image. This is really useful as when it's something they can also use with the intersection observer and do some other really cool things. Like I said, this is a nice way to optimize your apps. You know, whether or not the WebP or the JPEG PNG is better or not, I can't say. I don't know how images wise how better they are, but they are I think a good file size, so they're pretty fairly small, maybe smaller than some JPEG images. Again, this is about squeezing as much performance as you can out of these applications that are meant to be run on devices. All right, so how do you work with progressive web apps with a JavaScript API? There are some considerations you have to have in general when you're building mapping applications, right? You want to provide an app shell when possible. Oops. You want to delay the loading of the map if you can, right? And this is basically if you can get away with showing something other than the map up front, then go ahead and do it. There's a lot of capabilities in the API. Just to give you an idea, these are the, I don't even know if these are all the type of layers we have in I think these are all the type of layers that we have in a web map or could be in the web map. And we don't know when we load a web map. We load the web map, we introspect it, and we find out, okay, I need feature layer, so I'll load that JavaScript module. I need a web tile layer maybe, or maybe I need a KML layer. I need to load these different modules at runtime to be able to make everything work, right? What portals are used in the web maps? Do I need to have authentication enabled because they're secured services? What capabilities are the services? Can I edit? Can I not edit? Can I do identify or query? Well, you can pretty much do those all the time. Is it hosted or enterprise? And there are Depending on the version of enterprise you're running, you might not have all the capabilities of a hosted service. So there's all this information you need. Does the data need to be reprojected, right? Is your base map in some different projection than the rest of your data, and now we have to reproject all the data to match that base map? So there are some different patterns you can apply. There's some really good documentation that will be linked in these slides to determine the app map pattern that you might want to use. I'm going to talk about using Mapless Apps, right? And this doesn't mean that there's no map in your application, but that the map is not the initial focus of the application, right? I can get away with showing something else before I show the map, maybe a search box, maybe a pick list, something. And once they've done something with that initial page, then we'll go ahead and show the map. The spatial task can be run in the background. So maybe the application I'm going to show you, I'm going to do a search for nearby businesses. It's going to run in the background while my list is shown. No map is shown, but I'll just have those tasks running while you look at the initial list that you get. I can delay the map loading. This also gives me the opportunity to use routing, whatever frameworks or tooling from application I'm using. I can add some routing in there. That's me lazy load the resources as well. So let's talk about this demo application. The nearby JavaScript application that I said uses the Mapless app pattern. So here's the repo for the nearby JavaScript application. It's got some really good documentation with it. You can see the features it has is geocoding. It's got categories it uses with geocoding. Has location for your device, calculate bearing and distance. The base map will switch based on whether it's day or night. And again, it's built as a progressive web app using Webpack, using the ArcGIS Webpack plugin. We have documentation on how to get your client ID and apply that ID into this application, how to do redirect URIs, and everything's in here. All right, and there's a link to the demo service itself. The demo application. So here is the demo application. And when this application first loads, you can see that I'm loading 13 JavaScript files. So right now, let's go ahead and refresh this. And when the page refreshes, you'll see that I get my UI to show up pretty quickly, right? So there you saw the kind of the app shell for the UI right there. It's just kind of a couple little dots. Now the data has been refreshed based on my current location. So that was the service worker at play. I had cached data in the service worker that was able to get pulled in immediately. But while that happened, I was also able to go out and fetch any new refreshed data in my application and then display that. I've loaded 13 JavaScript files. There's no map here. I've only got a list of restaurants and so forth that are nearby me. Now, if I go ahead and click on one of these, I switch over to the map, and now I'm loading all of the JavaScript files that are necessary to be able to display the map and to also do the highlight and everything else. And I've got a pop-up in here. I've got the ability to filter these results, the places by the category, and I can always go back to the initial list and then back to the map and so forth, right? So this gives me the opportunity to lazy load a lot of JavaScript, a lot of CSS, and a lot of resources. This is a really cool feature you can use when you're building your web applications. Now let's take a look at some code and how something like this works. So this is a file that, make it a little smaller. So this is the main file that loads my map, creates my map and my view, and it does a lot of work related to the actual application. This application itself is built on React. You'll notice that there is no reference to React in this map application here. Also, if I go to the component for the map, my web map view React component, I don't reference the JavaScript API in here. I have some hooks to help me work with the web map, and I'm just going to go ahead and use these hooks to tell the JavaScript API, oh, here is the DOM element I want to display the map on, and so on. And in those hooks, if we come down over here, I have a use web map hook. The use web map hook is going to go ahead and lazy load that JavaScript file that's doing all of the work with the JavaScript API. So I'm not referencing those resources right away. I'm going to lazy load all the mapping JavaScript files I need after the fact, right? Not until I need them. So I have when I load the map, even as I add items to the map, update the base map, and so forth. And these are all, this is just some custom hooks that I've written for the web map to get nearby locations, right? So I'm saving some stuff in local storage to pull them up right away. Lazy loading, again, some other modules that interact with JavaScript API to find nearby places, right? So I'm doing all this really cool stuff. Even my authentication is a custom hook that I can build and lazy load as needed, right? So that's a really cool way that you can work with your applications. I highly recommend that you have something like this in your apps, this data folder that's going to have modules that are going to interact directly with the JavaScript API, do all the heavy lifting of the JavaScript API, but can be lazy loaded anywhere at runtime based on the framework or UI tooling that you're using to build your applications. I also wanted to show the audit for this page. So you can see here that I ran this audit on URL using web.dev, ran my audit, and I've got 99 for my performance, which is awesome. I have 92 for best practices, 90 for SEO, and I've got 69 for accessibility. With this one, I take a hit because I am requesting the geolocation permission when the page loads, meaning that as soon as you open the app, right away I'm going to ask for permission to get your location so I can find nearby places to you. I could change this to be like a button to say, hey, find places nearby me, and I'll be able to improve my accessibility score here. I've also got some SEO hits I'm taking on accessibility here as well. Oh, I'm sorry. This is my accessibility score here. What was that one? My bad. Those were in general. Oh, my best practices. That's what it was. So that's why I got a hit there. In accessibility, I take a hit because my actual colors aren't, to the best they could be. The contrast isn't great. I can improve those. I didn't add a lang attribute to my HTML, which my bad. I should have done all that. And these are things that I should have. I can update pretty easily to get a better accessibility score, which I will do. And with that, I'm going to go ahead and hand it over to my colleague, Andy, who's going to talk about the mobile web and how you can improve performance of your apps. And these are ways you can improve performance in general for your applications. And if you build your app with mobile ahead of time, think about that performance, you're going to get great benefits on desktop performance as well. Andy.
Hi, I'm Andy, and I'm going to be talking about improving performance of your mobile web applications. And I'm going to focus on two areas of performance. The topics that I'm going to touch on are going to look at the initial load of your application and things you can do to speed that up, as well as things that can improve the general user workflow after the application has been loaded. And I've included a screenshot down here at the bottom, which is the Chrome Performance Monitor, just to familiarize those of you who aren't familiar with this, of the CPU usage curve for just a typical mapping application is that this was the initial load, and that there's a lot of processing going on after the initial load, and then the usage tapers off. So we'll look at how to improve that curve and some best practices that your application will perform well in all situations. So my recommendations are going to fall into 5 buckets, and we're going to look at understanding your visitors, lazy loading, using fewer map layers where possible as well. We're going to talk about the difference between visible and removing layers, and a few suggestions on simplify, simplify, simplify. Now, I always suggest to my customers, know who your end users are, and there's no better way to find out that information than to analyze the web server logs. Ask your IT team for help, And analyzing the site visitor information, there's things you can do manually, there's free software you can use, there's paid software you can use to find out what type of browser they're using and the versions, the device types that are visiting your website, whether it's desktop or mobile, such as Android or iOS. You can look at the percentages of how many of your visitors are mobile versus desktop and which pages get visited the most, and so much more. And here's an example of the type of information that is in the web server logs. And you get information such as what pages are being visited, and perhaps most importantly, as it relates to this technical session, is the user agent string, which is roughly starting from the Mozilla 5.0 through Safari. You can copy and paste this information straight from your web server logs into a browser, and it gives some very useful information. So let's take a look at this particular user agent string that came in to our website, and some interesting things right off the bat. This was a Windows 7 device, which is no longer supported as of January 1st, but here it is. It's in our logs. Someone's using a Windows 7 desktop machine to access our website. And there's other information in there that you can glean to determine what type of functionality you're going to put into your website. Now, fortunately, this particular device does support JavaScript, but if we scroll all the way down, we'll notice that it does not support CSS4. So these are the types of things that can be taken into account when building your applications. Building mobile applications also means how well the application responds under a wide variety of conditions. And I'm specifically talking about the user interface performance here. We've all used applications that at one time or another, the application user interface either froze or it stuttered or it was sluggish. And research has shown that users will notice any operation that's longer than about 16 to 17 milliseconds. So that's when an application's working perfectly, it's running at 60 frames per second. And if it dips below that, the users are going to know that something's going on. This is a very short period of time, and oftentimes in GIS we're working with large amounts of data, but the ArcGIS API for JavaScript, we've done tons of improvements under the hood to help you reach this goal. And what we're talking about today is the things that you can do to help the application as well, and I'll show a demonstration of this shortly. So one of the first things you can do is reduce the size of the initial application load. And one of the easiest ways to do that is to defer the loading of modules if you don't need their functionality right away. Let's say you have some sort of a widget that does a geometry buffer calculation, and you don't need that at initial load. You really only need it when the user clicks on it. That's something that can be easily deferred. And if there is a single point to hit home on this particular slide, it's that not everything needs to be asynchronous. When you try and jam all of these modules through all at the same time, it can overload the CPU. Now, modern internet connections are usually pretty fast, especially when you're working at your desk, but if you're in the field and your end users are using an cellular internet connection that isn't quite perfect, then by doing these deferments like this can have a huge impact on the end user's performance. So let's go ahead and take a look at a demo. I'm going to go ahead and load this application, and I'll bring up let me close that. I'll bring up the network tab. This is going to be really small, so I'll try and fit it all in here. May have to adjust a couple of times so that we can fit it all in. And essentially what I have here is just a button. Oops. Trying to adjust it. Nope, it's not going to let me adjust for the code there, so I'll just have to show it on this particular resolution size that we're using for the video capture. So I have a button, and then when the user clicks on this button, I'm going to defer loading the geometry engine as shown here. I run the requires statement, which means it's going to go ahead and pull down the geometry engine module. I'm going to run a buffer around the center of the view and then draw that on my map. So I'll go ahead and click that, and it drew my buffer. Let's go ahead and take a look at the log. And here you can see that it did download the geometry engine. What's unfortunate with this screen size resolution is you can't quite see that this geometry engine is about 659K unzipped. What you're seeing here is the, oh, there we go. It's a 659K unzipped. So we pulled 156 kilobytes over the wire, and then the JavaScript parser had to parse almost 3/4 of a megabyte. And by lazy loading this in our application, we've deferred that so that it is only done when the user needs it. You can defer other things too, such as layers. And layers can often pull down a lot of data. They can use a lot of memory. So the typical thing that we'll see is that people will load all the layers immediately up front using this pattern as shown here, but you don't have to do that. If a user doesn't need a layer till later, then you can defer it by simply using map.add as shown here, and an array of layers, or just map.add many and add an array of layers, or just map.add to add a single feature layer, and it'll load it on demand when you need it without having to load it up front. So let's go ahead and take a look at a web map. So here's a web map of demographic data related to education in Mexico. And as you can see here, there's many other layers in this map. And right now, I have simply selected a single layer. So let's go ahead and open up my second demo. Here is an ArcGIS API for JavaScript application that is consuming that web map. And it recognizes that the web map only has this one layer visible. So what we're going to do is go ahead and load this app and just take a look at how much data is being pulled down with that single layer. And there's the layer loading. About 19.7 megabytes of total resources with just that one layer activated. So let's go ahead and go back to the web map, and I'm going to go ahead and turn on all these layers so that they're all visible. All the data is going to be loaded at the same time. I'm going to go ahead and save that. Then we'll go back and reload our application, and we'll just compare the amount of data that's being pulled across wire. Now it's not going to be a huge amount in this case. For this purposes of this demonstration, we didn't have time to wait and download dozens and dozens of megabytes, but you can see here it's now 20.8 megabytes in resources that have to be processed by the application and pulled down across the wire, and everything loaded before the end user can get access to that. So fewer layers means faster loading, up front. There's going to be less memory used by the application. The more data that you pull down in your application, that's going to be more memory used. There's less GPU and CPU parsing and rendering to load all that up front. So as you can see here, very simple demo, just a small amount of data we're talking about here. But if you have dozens and dozens of megabytes worth of data that you're pulling across the wire, across multiple layers, that's going to affect the loading performance. It's going to affect the end user's performance, and it's going to put a greater load on the GPU and the CPU to parse and render all of that information. So now let's talk about visible versus remove. And if you just need to temporarily remove a layer from the display, layer.visible property means that the features are still in memory, but they can be made visible or invisible as needed without requerying, without a round trip to the server. If you need the layer removed for a longer duration, or you simply don't need it at all, if you need to remove it, then the map.remove method will completely remove that from your map. And depending on which browser you're using, eventually, at some point, that should be garbage collected and the memory should be freed up. So let's go ahead and take a look at the code for that. And then I'll show you the application. So I have a feature layer, and I have a button toggle that says you can make it visible or invisible. And as you'll see here, so feature layer dot visible, I can set that property to false, or I can set that property to true, and it'll still be in memory. It will just hide its visibility. If I want to completely remove that feature, then I use the remove method on my map. Sorry, I said feature, but feature layer. I can completely remove it and then add it back when I need it. And when I add it back after removing it, it will completely reload those resources. So let's go ahead and take a look at that in a browser. And from the end user perspective, it looks like you're simply just making it invisible. Here's my visible, invisible button. And then I can completely remove the layer, and I'll go ahead and bring up my network console. And when I add that layer back, it is querying these features and pulling that data back down. Also, this is one of the most obvious things that we work a lot on, and it's the ability to simplify your data. So let's go ahead and take a look at this demo. See if I can get the browser to capture the number of features here on my screen recording. I'll adjust that around a little bit. So you can see here, this is zip code data in the United States. And for this particular zoom level, we're running at about 60 frames per second as I pan and zoom. And even though I only have a relatively small number of features, 264, there's 38,634 vertices. So let's go ahead and zoom out a couple times, and it'll recalculate. So now with this data, the ArcGIS API for JavaScript has a tremendous number of improvements under the hood for the latest versions of the 4.x API in terms of rendering performance. But one of the things we like developers to keep in mind is that just because you have a certain number of features, what's really important is the number of vertices that are inside those features. So the density of the data. And as you can see here, now we have about 30,260 features. However, the number of vertices is 528,929 that are having to be displayed and rendered as I move the map around. So more features is going to be slower load performance. And more features at some point, you can eventually reach the point where you're just overloading that particular browser, uh, whatever that number is for your particular machine and your internet connection, you can overload a browser at some point. So minimizing the number of features and within those, the number of vertices is the right way to go to simplify your data to get the best performance. So you can generalize and reduce the number of vertices. You can set the max zoom out level. You saw in that demo, as the further I zoomed out, the more features there were and the more vertices that I had to manage and render and hold in memory. And so by reducing those, reducing the end user's ability to zoom out and capture too many features can definitely improve performance depending on your depending on your feature density. Also, something that's sometimes overlooked when customers are hosting their own services is making sure that the web server has compression enabled. Oftentimes this isn't enabled by default and it can be gzip or Brotli. We use Brotli in ArcGIS Online for compressing services, and you might get some additional performance out of that if that's something you're able to look into. And also to use ArcGIS Online hosted services. This is a plug for ArcGIS Online, that it is highly optimized in terms of using a CDN and caching and the types of feature tiling that is used, which we don't have time to cover here in this session, to bring down the data to the client in the fastest manner possible, and it's highly optimized for that. Last but not least is test, test, test. One of the most common gotchas for mobile is not testing on a wide variety of devices. And this doesn't necessarily mean that you have to hook up an Android or an iOS device to your development machine and debug it, but definitely it means testing apps over cellular internet connections. And that means turning off your Wi-Fi, taking these devices outside the building, testing them in a variety of geographic areas to see how well your application performs. And one of the tricks that we use, I often hear that certain organizations only have very specific test devices. Now, if you're just talking about load performance and general usability of the application, grab phones from people in the office. Ask if you can temporarily borrow their phone, and you want to test on newer devices, which are going to be faster, and older devices, which are going to be slower. But you want as large a variety of devices as possible over cellular internet, not Wi-Fi, to make sure that you understand how that application performs. And with that, that's all I had for performance. I'm going to turn this over to Thomas, and I hope you enjoyed this section. Thank you.
Thank you, Renee. Thank you, Andy. My name is Thomas Oder from the Esri R&D Center in Zurich, and I would like to talk to you today about best practices in 3D. So we've seen progressive web apps, a little bit of information on that, and on the mobile web, and now the 3D part of this presentation. So performance can be limited on one hand by the processing power of your GPU. We can, for example, upload a single geometry and tell the graphics card to render that same geometry in 100,000 different places, which will primarily hit the processing power of your graphics card. This is a very typical bottleneck on desktop PCs that we see nowadays. Or we can envision a scenario where the geometry is a bit more complex, but we have a lot of textures that the graphics card needs to store and rasterize, and while the rasterization performance on modern mobile devices is comparable to desktop PCs, the amount of available memory on mobile platforms is severely restricted. So this section of best practices in 3D therefore needs to find a good balance between sheer compute power and available memory on these devices. So we will look at scene layers and tiled layers, symbology considerations, a look at a concept called elevation alignment, at a setting that we call quality profile, another setting that we call environment, and last but not least, at resource info, which is information that we expose with the upcoming 4.15 release that will help you to get a grasp on the amount of resources that the 3D scene view is using currently. And I will conclude by showing you a small demo that I wrote for visualizing performance in the 3D scene view. All right, so let's get started with scene layers. So scene layer are the primary layer type for 3D content. It allows streaming of large-scale data due to a process called cooking, which splits geometry into small packages that are easily transmitted on the network. This cooker implementation has a large impact on performance, since the better the data is partitioned, the more efficiently it can be streamed and visualized. Thus, using newer versions of Pro or any other cooker is beneficial when you publish your data for the web. So in this snippet here on the left, I show you how we are typically loading a scene layer with the scene view. So the scene layer class gets instantiated with the URL parameter that points to a scene server. And then we create our typical view. We give it a div, like a DOM element, that it should render into. And then we configure a map. We tell it to use a topological base map. We tell it to use world elevation as the ground, and we add that scene layer that we created on the top to its layer collection. So let's take a look at how this looks like. So here I loaded a San Francisco scene layer that we can see is streaming in as I move the viewpoint. And you might imagine that there's a certain logic to the way we stream in this data, and this logic is tightly bound to the cooker that published this data for us. Now, if I hit this play button here, I will kind of halt the view and or the updates of the rendering and just visualize the nodes. So here you can see that these green boxes, they are basically what the cooker partitioned from the complete geometry out into a small package or small parcel that can be efficiently transmitted over the network, and where we in the view can make decisions on whether we need to load that data or not, depending on what you're currently looking at. So this huge data set that might have been terabytes of data has been split down into these smaller chunks that are efficiently streamed over the network. All right. Next, I would like to talk a little bit about tiled layers. They've been at the core of GIS for a long time, and in many ways they are similarly partitioned into smaller packages as the scene layer that we've seen before. We call these tiles in the tiled layer case. And again, we do this to efficiently stream this data across the network. The number of loaded tiles obviously has an impact on your memory consumption. So the fewer, the better. Let me explain you this snippet. So we do the same thing as before. We instantiate the scene view. This time we don't load any particular layer, since the tile layer that we're interested in right now is actually in the base map. And the question here is, do you really need to see the sky, since the more you tilt the view, the more tiles you will have to load. So if I hit the play button, I will constrain the tilt, which is actually what you might want to do. and then I will again visualize the tile borders. So let me do that. And I stop rendering here, and you see this is the amount of tiles that I have loaded currently. Let me unfreeze this view and tilt to a rather uh, shallow angle and freeze it again. And if we take another look, then you kind of see that we are currently rendering many tiles, and the amount of tile image data is massively bigger than in the tilt constraint view. All right, next I would like to talk about symbol complexity. So symbolization of, for example, point data is an essential concept of GIS applications. Often a very large amount of data is present, and it's desirable to display as many points as possible in certain scenarios. We offer different types of symbology for you to choose from. Icons, for example, are basically bitmaps that use very few vertices. I could say just a quad, essentially, but require these bitmaps to be uploaded to the GPU and may therefore hit your memory limit. Primitives in the middle row here, like spheres or cylinders or cubes, they are geometrically slightly more complex, but don't incur the texture penalty that we might see from icons. So they're typically a good choice for 3D applications. I would also roughly say that the amount of vertices is in the order of less than 100, or roughly 100. Maybe not for these primitives that we show here, but there are other primitives that we offer in the API that are a bit more complex. And then at the top of the food chain, so to speak, are 3D models that allow you to load custom geometry by using the GLTF format, or you can choose from a gallery of available web style symbols. The number of vertices is generally speaking high, so in the order of thousands, and will thus hit the processing performance of your graphics card. To avoid to render too many vertices, the web style symbols come with different level of detail representations. Choosing the total number of rendered vertices that is optimal for the scale of your current view is performed automatically by the API if you use these web style symbols. So let me just quickly toggle through these different kind of symbol complexities that are listed in the list on the left. So this is the primitive, just a cube in this case. And then the next higher up one would be the card that I depicted here. And while you see that there is a slight performance hit on the machine that I'm working on right now, older computers with older graphics cards and also some mobile devices that are a bit older will actually show a clear decrease in frame per seconds if you have more vertices in your geometry. All right, the next topic that I would quickly like to touch is elevation alignment. So since 3D data implies a z-coordinate, the JavaScript API for 3D scene views offers you to do elevation alignment of z-coordinates on your content. There are 3 modes available. There is the absolute height mode, which uses the z-value as provided by the content. No additional computation is performed. This is thus the fastest mode that we offer. There is relative to ground, which will align the z-values of your data to coincide with the ground elevation at any given point. In order to do so, for every data point, we need to sample the ground elevation, which might introduce a noticeable performance penalty for large data sets. Last but not least is the relative to scene elevation mode, which will not only align your data to the ground, but also to any scene layer content that is currently loaded at the position of your data point, meaning that not only elevation data needs to be sampled, but also scene layer data. Obviously, this is this mode incurs the largest performance penalty out of these three modes. Then, as I mentioned in the beginning, we offer certain entry points for you to kind of instruct the API how resource heavy it should behave. One of them is the so-called quality profile. Setting the quality profile on a scene view allows you to instruct the API to shoot for lower or higher memory consumption, essentially. This setting affects the level of detail choices for geometry, image resolution choices for image-based resources, and also controls hardware settings of your graphics card. So in this snippet on the left, I kind of define these three profiles, low, medium, high, as they are required by the API to be set. We have our scene view. Initially, we load it with a low quality profile. And then if I hit the play button, I will just toggle through these profiles. So currently we're low. If I push the button, we go to medium. You see it updates. The tile base map layers got a bit more fine-grained. The geometry got a bit more fine-grained. Let's go to the high level, like even higher grade geometry. Maybe the difference between medium and high is not all that noticeable to you. For sure, if you set it to low, you will optimize your app or the way you provide your content to be accessible throughout the most various devices that are out there. Next, I would like to quickly talk about environment settings. These are similar to the quality profile in the sense that allow you to control the amount of resources that should be allocated for rendering. They allow you to control the level of complexity for the computational model of the atmosphere, for example, whether shadows should be computed, and if ambient occlusion calculations should be performed. So here in this snippet, there are, again, these profiles that I select from the array that I defined on top. And then I set, or first I read, but later I'll set the view environment atmosphere, which toggles the atmosphere complexity, and the lighting, which contains the shadows and the ambient occlusion. So let me switch that to high. You will immediately realize that there is a quite different representation. So again, here on this hardware, we are still rendering at 60 frames per second. What we are on an NVIDIA graphics card here right now. On an integrated graphics card, for example, we would already drop down to 50 frames per second in the high quality mode with shadows and ambient occlusion. Okay, so this brings us to the resource info section. As I mentioned in the beginning, the scene view exposes with the upcoming 4.15 release for the first time information regarding resource consumption as estimated by the 3D scene view. The exact numbers vary from hardware implementation to hardware implementation. Furthermore, browser vendors actively prohibit precise measurements of this kind of data for security reasons. That's why we can only provide estimates, but these have been engineered as closely as possible to actual resource consumptions as reported by debugging tools and operating systems. Let us quickly take a look at what kind of resource information data we are exposing. So the total amount of memory available, this is controlled by the quality profile. We actually can't get that information from the browser, but depending on which quality profile you choose, you will kind of set the limit for the total available memory. Then used memory is our estimate on all the resources that are currently loaded and to what amount of memory they kind of sum up to. Quality is our metric for telling you if we think that we had to drop the quality because of resource limitations. So say that we load a scene layer and we would like to render the scene layer at a higher resolution, but we can't because we hit the memory limit. So we actually show it in a worse geometrical representation that we think we should, and we kind of communicate this drop in quality through this number. Then the load property of the resource info will just give you a hint on how many things are currently happening in the API, what the number of tasks that we need to work every frame is currently. Then terrain memory will give you an estimate on the memory used by our terrain rendering engine, which contains elevation layers and tiled layers. Edges memory is another memory number that we expose. This one tries to account for the amount of memory that we think we're using to show you sketched edges or highlighted edges as available through the edges renderer in the scene layer. And then for each layer that we have loaded, we will show you certain information like which layer it is and the amount of memory that this current layer is using. All right. This brings us to the demo. You can access this demo here if you would like to play around with it on any of your devices to see how the performance on the devices that you know and are familiar with looks like. Let's step into it. All right. So in this demo, you have frames per second counter, and you have the ability to toggle the elevation layer, the base map tiled layer, the scene layer, the feature layer, and I kind of chose certain things that I think are interesting. So here we have like a normal elevation layer and a custom elevation layer that exaggerates the values that should be used. Let's turn that on. And you see that this elevation layer now came in with what we think is 262 kilobytes. Then the scene layer and feature layer I will show you a bit later. And then I also allow filtering here. With the filter, you can set a server-side filter or a client-side filter, and effectively we're just reducing the amount of geometry that we need to load in this case. Then down here in the lower left, you see those numbers that I've been talking about before. This is basically just a DOM representation of that resource info property that I explained just a second ago. So we have our total memory that we think we can use, and then these numbers. Yeah, and down here on the lower right, we have like a little scenario generator. So let's kick it off. And here, ooh, oh yes, we should maybe not use exaggerated elevation data to render this. Here you can also toggle the camera. Let's do this quickly. So this is just the New York scene that we kind of like to show for scene layers. And let's quickly play with the filters. Let's turn off the base map so that you can see a bit what the filters do. So here we have a client-side filter which restricts the geometry to a certain area. I can also toggle a server filter which will restrict the scenario or the geometry loaded to a certain criteria. Like for the scene layer, it's the height. For the feature layer, it's whether the restaurant has a web page or not. Let's keep the animation going now. Let's load that base map again. And you see that we're kind of being at those 30 frames per second that we should shoot for, even in a somewhat complex scenario like this one. And if I say, for example, turn off the scene layer, turn off the feature layer, you see that the frames per second increase. If I were to turn off the base layer, we get like very fast. We're up to 60 frames per second. So let's get them back on again. All right, let's toggle to our next scenario. So we have cars which get replaced by sailboats. And let's turn off all filtering just to make it as heavy as possible. I'm also being on relative to scene elevation alignment mode. And we are kind of still at those 30 frames per second, which is good. Now let's go to another scenario here. Stranded boats that will become trees. And here we're circling Liberty. What I wanted to show you here is the level of detail that we do for the web styles. So currently you see the trees are very coarse, and once we go a bit closer, you will see that we'll load a better representation of the data. Whoa, closeness. And again, down here in the lower left, you can see the memory consumption. Let's maybe stop the camera and go downtown just to kind of load a lot of data. Then you will see that the numbers here are actually going up quite considerably. All right, and now you see that we're at 60 frames per second, which means that we're not loading anything anymore. We are kind of stable. And we're shooting for 60 frames per second with the scene view in a static view like this. And as you've seen before, we're kind of trying to do as good as possible to not hit below 30 FPS performance hit. But this depends on the stuff that we need to stream in through the network, as well as obviously your hardware performance. And the complexity of the scene, as I explained before. All right, so that was it for the demo. Thank you so much for tuning in, and enjoy trying to find a good resource usage for your scene.